Okay, we're going to begin our exploration of the electrostatic model. We're going to use this exploration to try to explain conduction and induction, two common mechanisms for charging objects. However, prior to starting the exploration, we're going to review our electrostatic model from our reading from the previous couple of nights. So let's begin that review. In the model, there exist two types of charge. There's the positive charge, and that's associated with the protons that reside in the nucleus of the atom, and there's the electron associated with the negative charges that reside on the outside the nucleus in the atom. So there's two types of charge. One's called positive, the other is called negative. In our model, we talk about neutral objects, or uncharged objects, which have equal numbers of positive and negative charge. It's important that you recognize that neutral objects are not objects that do not have any charge. It's just that they don't have an imbalance in charge. There's an equal number of positives and negatives. So let's look at, here's an example of our balloon that just floated up. It's represented with 10 positive charges, which actually represent billions and billions of protons that reside on the atoms that make up and the molecules that make up the balloon, and an equal number of electrons, an equal number of negative charges, and we're representing that by the 10 negative or 10 green negative charges. And so even though this object is very much has a lot of charge on it, it has an equal number of positive and negative, and we would then say this object has no net charge. Sometimes people say no charge. That's not correct. It's no net charge. There's no unbalanced charge. In this case, we have an object, a balloon floating up, and notice it is missing some negative charges. Again, it has the same number of positive charges. In our model, the positive charges are rigidly held fixed within the solid. It's part of the nucleus or the core of the atom. The negative charges outside those cores can actually be sometimes on some materials moved around, taken away, added to, and in this case we've removed a certain number of negative charges from this matter. It has, in fact, on our representation, the 10 positive charges, 6 negative charges, so its overall state or unbalance is positive. And we would say it has a positive 4 positive extra charges, or excess of 4 positive charges. Another way to say that, it has a deficit of 4 negative charges, but we'll call this a positively charged object plus 4. Let's look at one more example. In this case, we have, again, the positive charges don't move, so it has 10 positive charges represented by the plus, and it has many more negative charges that have been added. The negative charges are the mobile carriers in our model, the electrons, and so we have 10 positive charges. We have used the computer to count, too many green negative charges for me, 17 negative charges, and we would say this object has an overall charge, or an excess negative charge. And in fact, quantitatively, we'd say it has 7 extra negative charges. Let's continue with our review. In our model, we say like charges repel. And so here's an example where we have two objects that either could be both positive or negative. Both objects are positive. Both objects are either positive or negative, and they repel each other. The force that this object here on the right is repelled by the object on the left is equal, by Newton's third law, to the force this object on the left is repelled by the object on the right. In our model, opposite charges attract. So if we have a positive charge here and a negative charge here, they would attract each other. Vice versa. This could be the positive and this negative. It doesn't matter, but they would attract. And again, the attraction that the red one feels from the green one is exactly the same as the attraction that the green one would feel from the red one. Regardless of how much charge is on each object, or regardless of the mass of each object, the force on one would equal the force on the other. But unlike charges attract, and Newton's third law said they would attract with equal forces. Our standards in this model are going to be a rubber rod rubbed with fur, and we will say a rubber rod rubbed with fur will acquire extra negative charges. So this rubber rod, if it was rubbed with fur, you should visualize with a fixed number of positive charges and an excess, a lot of extra negative charges on it after it's been rubbed with fur. By the way, that would tell us that the fur actually now has an excess of positive charges, because charge is conserved in our model, so any extra charges that are picked up by the rubber rod must have been lost by the fur. Another one of our standards in our model is a glass rod rubbed with silk, and we would say a glass rod rubbed with silk would acquire net positive charges. Again, there's a fixed number of positive charges in here, so really what's going on is negative charges were stripped away from the glass rod, so it acquired a net positive charge. We then could also deduce from the conservation of charge that the silk must have picked up these extra negative charges. In our model, we will also classify materials as either insulators or conductors. Insulators are materials that do not allow electrons to flow easily. So insulators, even though in our model we say the electron can move readily, there are certain kinds of materials, classes of materials called insulators, where even the electrons are not able to move very readily to flow on its surface. So an insulator can become charged. It can acquire extra negative charges, but once the negative charges are on that object, they aren't readily or they aren't easily able to flow around that object. We will see in conductors they can. So insulators do not allow electrons to flow. Please remember, they can acquire a net charge, but the electrons will not flow easily. Rubber, plastic, glass, dry wood, oils, etc. are all good examples of materials that act as insulators and will protect us from, generally protect us from electric shock. An example there is the glass being used on a electric line or a transformer line, so that it can be moved without actually touching the conductor that runs down the middle of that cable. Wood is an insulator, rubber is an insulator, so people working in electrically charged situations often wear rubber boots to help keep them from having the electrons flow through their body and into the ground. There's another example of an insulator holding a wire that's carrying a lot of current, a lot of voltage off of the tree, so it's keeping it from contacting the wood or any other materials. And then we see rubber around wires so that we can clip the alligator clips without actually touching the conducting metals. So conductors are materials that allow electrons to flow easily. We saw in a couple of the last slide, these materials also can acquire a net charge, but when they do acquire a net charge, the electrons can easily flow through the material, on the material, and then hence be transferred for other objects that may be touching it. Metals are all good examples of materials as conductors. We know that you're told to keep away, the danger of keeping away from electrical wires, and the electrical wires have insulators around them so we can actually touch them without the electricity flowing into our body. There's another example of a wire. Gold is an excellent conductor, and in cases it's expensive, but in cases where you really want to have the electrons to be able to flow very easily without any loss, gold is often used as the conducting material. And for instance, a very high-end computer circuit, the connecting wires between the different components of the computer may actually be soldered in gold or placed in gold. There's a third classification of material which we call semiconductors, and these are materials with conducting properties somewhere between insulators like glass and conductors like copper. And antimony, arsenic, boron, carbon, germanium, selenium, silicon, sulfur, and tellurium are materials that can be made to act like semiconductors. These are very important materials. As we know, many of our electrical devices are made with semiconductors such as silicon chips, which is being shown in this slide. So it's a very important class of materials. It's not a class of material we will do a lot of work with in this particular unit, however. We will look at more conductors and insulators in this unit. The equipment we will use in our exploration is shown below. There's the fur and rubber rod. That's our standard for rubbing rubber rod with fur. Produces a nice negative charge on the rubber rod. Remember, it always has positive charge too, but those don't move, so it gets an excess of negative charge by rubbing it with fur. The fur will actually lose negative charge, the conservation of charge. We will also be using silk and glass rods, and the glass rod rubbed with silk from our standard. The glass rod acquires a positive charge, and actually what's happening is it's losing its negative charges to the silk. Again, remember, positive charges do not move in our model, only negatives are transferred between materials. The final device, which is new, you haven't seen before, is an electroscope. And I want to talk a little bit about that electroscope now and what it's made of. It's made up of both conductors and insulators. And as we look at this larger view, we see that there's this metal conductor on top of the electroscope, and then there's this metal rod running right down the center core of the electroscope and is attached to another metal device here. There is an insulator material between here and around here, so that any electrons that are on this metal piece or flowing on this metal piece cannot escape through this ring or out through this ring out here. It's also an insulator here. Notice there's also another device here. There's a little pin hinge here. This is also a piece of metal that is connected conductively. It has a conducting path that goes down here. It goes through there and up in there. So the electroscope essentially is a long conducting path protected from the environment that has this lever arm that is part of the conducting path that actually could pivot out from this middle arm. So that's an electroscope, and we'll see a lot more about the electroscope as we actually begin the exploration shortly. So we'll stop this movie and go back into your unit and click on the second movie when you're ready, and that will be the beginning of our exploration. I hope you enjoy it. It should be lots of fun. And remember, keep in mind all the ideas that we presented in the model that we just talked about. Great. Thank you.